Good morning and welcome to Branson Legacy Sabbath School. Today we have a special treat that I hope is going to elicit a good discussion and lots of interesting thoughts. But before we start, I'm going to ask Dorothy to lead us in Bible reading and prayer. Thank you, Dorothy.
Good morning, and I'm starting with Psalm 19. The heavens declare the glory of God, and the firmament showeth his handiwork. Day unto day uttereth speech, and night unto night showeth knowledge. There is no speech nor language where their voice is not heard. Their line is gone out through all the earth, and the words to the end of the world. In them he hath set a tabernacle for the sun, which is as a bridegroom cometh out of his chamber, and rejoiceth as a strong man to run a race. His going forth is from the end of the heaven, and his circuit unto the ends of it. And there is nothing hid from the heat, therefore, thereof. The law of the Lord is perfect, converting the soul. The testimony of the Lord is sure, making wise the simple. The statutes of the Lord are right, rejoicing the heart. The commandment of the Lord is pure, enlightening the eyes. The fear of the Lord is clean, enduring forever. The judgments of the Lord are true and righteous altogether. More to be desired are they than gold, yea, than much finer gold, sweeter also than honey, the honeycomb. Moreover, by them is thy servant warned, and in keeping of them there is a great reward. Who can understand his errors? Cleanse thou me from secret faults. Keep back the servants also from presumptuous sins. Let them not have dominion over me. Then shall I be upright, and I shall be innocent from the great transgression. Let the words of my mouth and the meditation of my heart be acceptable in thy sight, O Lord, my strength and my redeemer. Now I am going to Isaiah. I wrote down my chapter. Isaiah 65, verse 17. For behold, I create new heavens and a new earth, and the former shall not be remembered or come to mind. But be ye glad and rejoice forever in that which I create. For behold, I create Jerusalem a rejoicing, and her people a joy. And that is the end of that verse. Shall we pray? Our Heavenly Father, we want to thank you for the end of the week. Some of us have had quite a week with snow, with other things happening in our lives that have made us sad. Please help us as we come through this class to sit back, relax, and enjoy the company of you and those around us. Thank you. Amen.
Thank you, Dorothy, for that excellent reading of the scripture. Thanks to Dave and Bronwyn. I'd like to welcome all of you to our Sabbath School and our feature and experience in the discussion of cosmology, Christianity, and the James Webb telescope. I have an airplane analogy this morning in my introduction of the RBLSS feature. But first, for our feature today, we'll have introductory remarks to set the stage for the videos we'll watch. I have not prepared slides to accompany the introduction. The videos that we'll see have very good graphic representations of some of the topics we're going to cover. But the airplane analogy from Dave and Bronwyn, with whom I spoke this week, is this. We are bringing the RBLSS plane in for a landing. Ladies and gentlemen, we've begun our initial descent. The captain has turned the seat sign on. Please buckle your seatbelts, put away your personal belongings, bring your seat backs to their upright positions. We should be landing shortly. Dr. David Larson, our veteran captain, will land the RBLSS plane next week. For our initial descent, beginning with today's feature and discussion, what are a few takeaways from our time together over the last 9 months?
So are they shutting down the Sabbath school?
No.
First, I'd like to draw our attention to a couple of things. The boundary conditions of cosmology and the origins of our universe. In the beginning, God created. God ended his work and rested. Number two, astronomers, astrophysicists, when asked what came before the Big Bang, readily concede they don't know. I'm going to make a categorical statement. I contend that we do know. Number three, the necessity of faith across the cosmological models is very evident. Number four, salvation by faith through Christ and all it embodies, including the gift of eternal life, signified by Christ's resurrection. Number five, the renewal of the universe through the healing vision of Revelation. Now to our feature. Just bear with me here. That's my... Cosmology is a complex but very important topic. It seeks to answer the question, how did we get here? How did things come to be? This is a fun and exciting topic for me because most treatment of cosmology origins is done with limited insights into thermodynamics by the research community. At bottom, though, the cosmology is an energy system, and mechanical engineers understand energy systems and thermodynamics very well. Dr. Stephen Chu, Nobel laureate and the former head of the US Department of Energy, and the William R. Keenan Professor of Physics and Molecular and Cellular Physiology at Stanford University observed the following, quote, mechanical engineers and chemical engineers have a far better understanding of thermodynamics than physicists. For good reason. Mechanical engineers live and breathe energy systems. There are two competing models of cosmology origins, or the origins of the cosmology. The first is what I call the Rand-Plotz model. Random processes, long time scale model. This model proposes that the cosmology came into existence by sudden, spontaneous, random quantum fluctuations. This model represents the resonance and accumulations of these random fluctuations igniting the Big Bang. Out of that entropy, order emerged. But at the same time, this order occurred under conditions of increasing entropy. This would seem to be somewhat contradictory. Let's reflect on that. This model is known as the standard model of cosmology. It is also known as the lambda CDM model or the lambda cold dark matter model. Many Christians embrace this model. There's an alternative model. I call this model the cosmology by articulation model, COBA, C-O-B-A for short. The alternative model claims cosmology emerged by articulation with the input of ordered information, embodied specifications, if you like, the expenditure of energy. The result is the emergence of structured matter and populated space-time by exponentially accelerated thermodynamic processes under reduced entropy, even entropy-free conditions. Many Christians embrace this alternative cosmology model. In my consideration of these matters, a very pertinent question arises. Which of these models is thermodynamically consistent across the history of the universe? It is interesting to me that the sampling of the cosmology literature lacks much reference to the standard laws of thermodynamics or the generalized law of thermodynamics. And by the standard laws of thermodynamics, I mean the following. The simple definition of work, which is W is equals to force times distance. The wave equation, in its very simple form, it is E is equal to the Planck constant, small h, times nu, the Greek letter that represents or symbolizes frequency of a resonant cavity. The definition of entropy, which is the change in entropy is a function of the energy and the temperature or the information state. In differential equation terms, it's small ds is equal to small dq over T, capital T, the temperature. By the way, participants of the digital foodless potluck are familiar with the long-form derivations of the equations above, including the associated quantum mechanics, which relate information to energy, to matter, and possible articulations that bring these into existence. I'll show the derivation slide during the break because this is a research topic and potentially might result in a paper. I'm not going to include it as part of the recording. Which of these competing models have withstood the test of time? Which of these models is observed and operate in everyday conditions? This is an important consideration because the laws of thermodynamics govern all space-time across the universe and are consistent across all entropy domains, entropic and entropy-free. It is now observed that the standard model, which proposes the spontaneous emergence of the cosmology by random quantum fluctuations, is challenged by massive inconsistencies. Researchers, including Brazilian astrophysicist Marcelo Gleiser, questioned the overall current view of the universe in the form of the standard model of cosmology. They note that the standard model is not aligned with recent observations made possible by the James Webb Space Telescope, JWST for short. We will hear more about the JWST in the video. In his paper titled, quote, "A Candid Assessment of Standard Cosmology," unquote, astrophysicist Fulvio Melia says, the standard model needs a complete overhaul in order to survive. As a result, the standard model of cosmology, which has informed the understanding of the universe for decades, has had to undergo a number of revisions and rethink. Several researchers have wondered if the standard model itself is, well, fatally flawed. I would note, however, that despite its flaws, the standard model has served an instructional purpose. It can be corrected. But an added purpose might be, if at least, that we humans shouldn't be so confident in our assertions about how the universe came into existence and exclude the role of the creator. What are some of these recent observations made possible by the James Webb Space Telescope that challenge the existing model of cosmology? And why do they constitute a crisis in cosmology? Astronomers, astrophysicists, and cosmologists identify at least 6, thanks to their analysis of the James Webb Space Telescope data. It is important to recognize that much is still being learned about the new JWST data. But let's review them quickly and then get to the videos. I will elaborate on some of the points and leave the rest to the videos. First, the unexpected fully formed galaxies existing 300 million to 1 billion years after the Big Bang. This observation is self-explanatory, and the first video will go into this. But briefly, analysis of JWST data by researchers have found fully formed galaxies in the early years after the Big Bang. The cosmological models have predicted 13 billion years or such long time periods are needed for galaxies to form fully. Second, the Hubble tension. This refers to the persisting differences in estimates of the expansion rate of the universe using two time-tested methods. Generally, two methods are used. Measure of the cosmic microwave background, and Cepheids, which are very bright stars, and the observation of their relative luminosity. I won't say much about this because the second video, which is 18 minutes long, will delve into it. Third, differences in the estimates of the S8 factor, which characterizes the clumpiness of the universe. Previously, it was thought that the cosmic microwave background radiation was smooth and uniform. It is now known that temperature differences across the fabric of space-time constitute ripples which affect the composition of space and the volume of matter. Assumptions about the stellar initial mass function also play into this. The initial mass function characterizes the initial distribution of masses of star populations. They're presented as probability distribution functions, and they describe the probability that a star will have a certain mass during its formation. This probability distribution function differs from the present-day mass function. The present-day mass function describes current distribution of masses of stars after some time following their evolution. But in the absence of sufficient number of young star clusters to determine the initial mass function, the present-day mass function is used and results in extrapolations back to the IMF. You can imagine what kind of uncertainties arise from those extrapolations. Fourth, quantum fluctuations. There are unresolved questions about initial conditions and entropy. Both define boundary conditions. Did quantum fluctuations truly originate spontaneously? Similar concerns as in 3 that I talked about before about the stellar initial mass function apply here. Generally, cosmology assumes origination in an entropic inertial reference frame. But what if a defining condition of the cosmology has a different entropy as a boundary condition? This is a non-trivial constraint. 5, problems with inflation, the universe inflating. Did the universe rapidly and violently expand at 10 to the minus 36 seconds, which is very less than 1 second, during this infinitesimally small period, cooled and stabilized at 10 to the minus 32 seconds as modeled? 6, too early black hole formation. And as you saw in the announcement, I quibble with the terminology quote-unquote black hole. It is one of those misnomers in science. These regions should really be referred to more appropriately as regas, or regions of intense gravitational attraction. As in 1, the James Webb Telescope, Space Telescope data suggest regas' existence in early periods of the universe that were deemed not possible or not predicted by the standard model. Let's now quickly return to the other cosmology origins model against the backdrop of recent understanding of the standard model, or the lambda CDM model. There are several things to notice about the COBA model. Remember, this is cosmology by articulation. First, it is thermodynamically consistent. Second, anyone familiar with the laws of thermodynamics can derive and grasp their implications immediately. They're self-evident. Third, the framework is observed in everyday circumstances. Fourth, it supports the idea of a built and populated environment. Indeed, we live in a built and populated environment. What are the faith and theological implications of these developments? There are several. and I hope we can discuss these when Monty moderates the Q&A. If you are a Christian who have embraced the random processes model as part of your outlook on cosmology, what now? If you are a Christian who embraced the Genesis version of cosmology origins, never mind the details and the physics of how the cosmology unfolded, how do you relate to the people in group 1? Third, does God's promise to remake the heavens and earth increase our confidence in his declaration that he created all things? He is creator. One of the assurances for me from scripture about the origin of the cosmology is that Jesus refers to the creation in the book of Matthew. Furthermore, Revelation 21 refers to the new heaven and the new earth. I like to think that as Christians, our embrace of the creation according to various references in scripture, Genesis 1, Psalms 19, is on solid ground. That claim of mine has a basis in thermodynamics. So very quickly, a reason to watch the videos is to observe that even if all that is represented is valid and supported, is information that isn't widely understood and assimilated by all. Therefore, faith is required to accept what is presented. We will notice that across the presentations, none of the presentations, less any errors, exclude a pathway by which articulations of the Creator could have embodied specifications of populated outcomes by the thermodynamic model of cosmology. The two videos were selected for two reasons: to help us see how the postulates of cosmology by the research community are just what they are, postulates. They're not necessarily facts. Compared to the declarations of cosmology by the Cova model and in Genesis, both require the exercise of faith, one less so than the other by the different levels of uncertainty. So the first video, as I mentioned, has 4 parts, but we'll only watch parts 1, 2, and 4. Those parts are titled Eyes to the Heavens, Part 2, the First Galaxies, Part 4, the James Webb Mystery. The second video delves deeper into the expansion rate of the universe and the Hubble tension. Keep in mind that much of what is presented is from the perspective of the entropic universe. Under this framework, the total entropy of the universe is increasing. This observation necessarily implies that at some point, the entropy of the universe was 0 and possibly negative. This insight supports entropy reversal and is consistent with the second law. It is also not necessary that these outcomes occurred over billions of years as represented. It is possible that under entropic conditions, as measured and estimated by these different cosmological models, that these billions of years in time interval could be surmised. Creation continues. When Genesis says God ended his work, it seems to me it refers to a specific work, not the end of the work of creation. As the video suggests, star and galaxy formation continue across space and time. Monty, please do us the honor and let's start the first video. Thank you.
On Christmas morning 2021, a mighty rocket burst into life. Quickly climbing away from the ground, it soared into the cloud-laden sky and headed for the darkness of deep space. Its target was 1.5 million kilometers from Earth, at a place where the gravities of the Sun and our planet combine in a very particular way. In this spot, known as the Lagrange point, the payload would be held in space, fixed in relation to the Earth as it circles the Sun. Once in location, this payload began its delicate deployment. Immense sheets unfurled to shade it from the glare of the Sun, as hexagonal mirror segments unfolded and clicked into place. It then waited until it cooled to the frigid background of space. After several months, the device was ready for operation. The latest in a long line of technological leaps, a signal was sent from the Earth for this most recent observer to awaken, to open its eyes and to peer into the darkness. After 30 years and $10 billion, the James Webb Space Telescope had finally arrived. James Webb possesses a 6.5-meter mirror and cameras tuned to see in the infrared. Its mission is to map the lives of young stars in our own Milky Way and hunt for life on planets in orbit around other suns. But it was its view of the early universe that caused the first controversy. The power of James Webb, sitting far from the glow of the Earth, is its ability to peer far back in time. Its sensitive instruments can discern light that has travelled for more than 10 billion years, emitted by the first stars in the first fledgling galaxies. Through Webb's eyes, we can witness the birth of the universe. Astronomers, of course, had expectations of just what Webb should see in the infant cosmos. Over the 20th century, they had come to realise that galaxies, even our own Milky Way, had grown over time. They start as small groups of stars, but through collisions and mergers, small galaxies grow larger, until, over many billions of years, galaxies with hundreds of billions of stars appear in the cosmos. But as astronomers pored over the new images from James Webb, something did not seem right. As they peered into the epoch of the earliest stars, they expected nothing but small, featureless blobs. But instead, they saw something unexpected. Large, well-formed galaxies peeking out of the darkness. Objects that made no sense. For since the turn of the 21st century, astronomers have believed themselves to be in an era of precision cosmology. They had determined that gravity in the universe was dominated by a strange, dark matter, and the expansion of the universe accelerated due to an even stranger, dark energy. Both of these have fed into the most accurate model of the universe we have, a model known as Lambda CDM. And yet, James Webb had revealed large galaxies appearing to exist in the first billion years of the life of the cosmos, going against the predictions of this hard-fought model. Some scientists have been driven back to the drawing board to revise their theories of galaxy formation, but others, much more worried, fear for the very foundations of our understanding of the universe. But this is not the first time that new eyes on the sky have demanded a revision of the cosmos. Since the earliest of times, people have looked to the stars to uncover the workings of the universe, and since the earliest of times, they have been surprised by what they saw. And so what do we understand about those first galaxies, forming in the black just after the Big Bang? And do these surprises thrown up by James Webb derail our understanding of the universe, or help strengthen its foundations even further? The first food eaten in space was a beef and liver paste that Yuri Gagarin squeezed into his mouth like salty toothpaste. He followed it up with chocolate sauce. This video has been sponsored by Factor, the best, healthiest meal delivery service out there, and an impossible dream for early astronauts. Their healthy menus are updated weekly and include more than 27 meals and 33 add-on options. You can choose your favorite meals, or let Factor craft your order based on your taste preferences and meal history. They offer keto, calorie smart, chef's choice, and vegan and veggie options, which is fantastic for me as I've been trying to cut down on my meat consumption. Factor takes the guesswork out of food shopping and meal prep, saving you time and energy for other things. The no-hassle prepared foods make sure you always have something nutritious on hand when you don't have time to think about making a meal. So head to factor75.com or click the link below and use the code HOTU50 to get 50% off your first Factor box. Thanks to Factor for supporting educational content on YouTube. The story goes that Galileo Galilei was the first to successfully turn a telescope to the skies. The device, a simple arrangement of lenses, had only recently been invented, its earthly employment having mainly been navigation, surveying, and of course, warfare. But Galileo's focus was the motions of the heavens. The invention of the telescope is implicitly tied to the birth of modern science. A little more than half a century after Galileo, Isaac Newton also turning his attention skyward. Replacing lenses with a silvered mirror, he revolutionized the design of telescopes, sharpening the image and constructing the forerunner of today's massive telescopes, including James Webb. But unlike Galileo, Newton's observations didn't revolutionize the cosmos, but his discoveries of the laws of motion and gravity certainly did. Now the orbits of planets, moons, and comets were understood not to be a sign of the divine, but the results of physical laws that pervade the entire universe. Astronomical telescopes steadily developed after the time of Newton, and through each advance, more and more light could be collected, the improvement of optical systems resulting in clearer and sharper images. Astronomers now had the tools to reveal the true beauty and complexity of the universe. And so, just what did they see? As well as stars and planets, the skies were often home to magnificent comets. And by the mid-1700s, French astronomer Charles Messier was hunting for these heavenly bodies. He was looking for the fuzzy coma of a comet, formed as ice and dust are boiled off the cometary surface. But in his search, he found himself constantly frustrated. We now know that comets are rocky, icy bodies that orbit the Sun, and Messier had expected the fuzzy coma to move night after night during the comet's travels. But he came across numerous fuzzy objects that stubbornly remained in place, not changing at all. Messier decided to allay his frustration by cataloguing all these anomalies, ignoring them if he happened to spot one. And so, though Messier's catalogue of 110 objects mainly contains simple clouds of gas within our Milky Way, unknown to Messier, many of his objects were much, much more distant. Throughout the 19th century, with better telescopes, astronomers had found structure in some of Messier's objects, swirling spiral patterns hinting the objects must be rotating. Eventually, two giants of astronomy went head-to-head to settle the question. And by 1921, a great debate on the nature of these spiral nebulae began. The protagonists were Harlow Shapley and Heber Curtis. In Shapley's mind, our own Milky Way was the entire universe, whilst Curtis argued that there were extremely distant individual galaxies lingering out there. Though the debate ended in stalemate, very soon the question would be settled once and for all. By the 20th century, telescope mirrors had grown to more than a meter in size, and in the 1920s, Edwin Hubble used the 2.5-meter Hooker telescope to survey the heavens. It was then that the scale of the cosmos grew immensely and definitively, as he proved that spiral nebulae lie far beyond our Milky Way, whilst the flow of galaxies away from us showed we live in an expanding universe. In a few short years, our view of the cosmos had been completely revolutionized and rewritten. Countless galaxies, each with billions of stars, were scattered across the universe in a cosmos no longer seen to be unchanging and eternal, but a dynamical place, expanding and evolving, springing into existence at some time in the past. The story of this Big Bang, our cosmic birth, has been told many, many times. And after the universe's fiery creation, we understood it was smooth and featureless. But this still left a question. Where did all the galaxies we see today come from? Just what forces sculpted the universe? Throughout the 20th century, telescopes continued to grow and scour the cosmos. More mysteries were revealed, dark matter and dark energy amongst the biggest, and by the dawn of the 21st century, 10-meter telescopes now stared into the darkness. These earthbound telescopes were complemented by telescopes in space, the most famous of these being the Hubble Space Telescope, put in orbit in 1990. Its mirror, only 2.5 meters in diameter, is small compared to the behemoths on Earth, but sitting beyond the shimmering effects of the atmosphere, it can see more clearly than the others. Over the last 3 decades, the sharpness of Hubble's observations has wowed both astronomers and the public, and posters of spectacular images are stuck to walls all around the globe. But not long after Hubble was placed in space and opened its eyes on the universe, plans for its replacement, a bigger, more powerful telescope, were put in motion. The mission had to be ambitious, pushing the limits of technology and striding past the view of Hubble. The planned mirror was to be so large it wouldn't fit into even the largest rocket, so it would have to be segmented and folded like scientific origami, and one of the most powerful rockets would be needed to fling it into the darkness of space. Through numerous delays and cost blowouts, this new telescope, the James Webb Space Telescope, found itself on the launch pad. And on that Christmas morning, 2021, it blasted away from the Earth. Astronomers have pinned their hopes on this $10 billion feat of technology and science, hoping to conclusively answer the biggest question of all. Just where did galaxies come from? How can you use a map of the universe to chart a course through the center of an atom? The James Webb Space Telescope is the latest in a long line of telescopes we've sent skyward. But it is not the strangest. That prize could well go to the Planck satellite, launched in 2009, and for its 3 years of operation, the coldest known object in outer space. At 0.1 degrees above absolute zero, its mission was not to look at stars or galaxies, but to map the entire sky. And counterintuitively, scientists have been able to scale down this multi-billion light-year wide map to plot the microscopic world, revealing the landscape of the beginning of time. Planck was the latest in a long line of satellites used to map out the cosmic microwave background, the leftover radiation from the first moments of the universe. This had been discovered in the 1960s, and Planck's goal was to hunt for ripples in this all-sky emission, tiny variations in the temperature of the cosmic microwave background across the universe. The temperature of the cosmic microwave background is about 2.75 degrees above absolute zero. But soon after its discovery, there were hints that this temperature was not the same everywhere. At about 1 part in 10,000 in temperature difference, this pattern of ripples was formed in the earliest moments of the universe, imprinted when the cosmos was extremely different to that we see around us today. And yet, despite this vast chasm of time, these ripples are essential for our very existence, as they reveal the ultimate origins of galaxies themselves. To seek out this origin of galaxies, we have to go back a very long way. Back to about 10 to the minus 36 seconds after the universe came into being, when it was nothing but a roiling sea of energy and particles. At this time, astronomers think that the universe drastically changed. The trigger is uncertain, but for the briefest of periods, the expansion of the universe exploded. Cosmologists call this violence inflation, an event that flattened the very space-time geometry of the cosmos. But by 10 to the minus 32 seconds, it was all over, and more sedate expansion resumed. The expansion of inflation froze and emptied out the universe. But as it came to a close, the immense energy of inflation flooded back into the vacuum, and out of this emerged matter and radiation, electrons, photons and quarks, smoothly filling space with the stuff of today's universe. But not totally smoothly, for there were tiny, almost imperceptible ripples in the cosmos, ripples that would end up being crucial for our own existence. For gravity reached out from these overdensities and began to draw in other matter. And it was these tiny overdensities that would become the gravitational seeds of the galaxies we see today. But where did these ripples come from? How far back does this origin story go? To understand the ultimate origin of galaxies, we have to pull the veil back on the very earliest moments of the cosmos, the time before inflation. In these opening moments of time, quantum mechanics reigns supreme. At the smallest scale, much smaller than the scale of an atom, quantum energy churns and roils, fluctuating in and out of existence itself. These fluctuations are unpredictable, governed by the probabilistic world of the quantum, and defined by Heisenberg's uncertainty principle. This principle says that energy can spontaneously appear from nowhere, as long as it rebalances and pays back its energy debt in the appropriate timescale. But the onset of inflation broke the harmony of this quantum loan system. The rapid expansion cuts off the repayment, and the quantum ripples in energy are frozen into space. It also inflates the size of the ripples from microscopic to macroscopic. And at the end of inflation, it's these ripples that are filled with the matter of the cosmos. And this is how we can use a map of the entire universe, the cosmic microwave background, to investigate the microscopic quantum world. Despite these vast changes, by the close of inflation, the universe was still very young. And as it cooled and expanded, it continued to evolve. At a millionth of a second, protons and neutrons solidified out of the particle soup, and at the 1 second mark, these began to combine into the first elements. By a couple of thousand seconds, these first steps of the universe were complete. The universe had expanded and cooled, and the nuclear furnace was extinguished. Slowly, these fires of creation faded and died, and the universe was plunged into an inky blackness. These dark ages would envelop the universe for 100 million years. But just like the dark ages of early medieval Europe, they were far from uneventful. Gravity's grip had grown tighter as matter flowed from the less dense areas into the denser regions. But just what was it flowing in the darkness? Of course, there was the subatomic soup of hydrogen and helium nuclei, along with electrons, photons, and ethereal neutrinos. But hidden in the black, there was more. Much, much more. For as well as atoms, the Big Bang had created huge quantities of other matter, matter that still dominates the mass of the cosmos today. In the darkness, dark matter had started to flow. As now, this strange dark matter dominated the gravitational pulls of the universe. And in the early universe, in the darkness, it was dark matter pooling into the overdense regions. The gravitational pull of dark matter was irresistible, drawing in nuclei, electrons, photons, and neutrinos. In the darkness, dense regions grew, and the first whispers of galaxies had truly begun. But matter followed a different path. Unlike dark matter, whose physics is extremely simple, gas is extremely complicated. Gas can collide and shock, heat, and, importantly, cool. And so when the universe was about 100 million years old, the gas was dense enough and cool enough to finally fragment. These fragments collapsed under the continuing action of gravity, and as they collapsed, the density of the fragments grew as they became more spherical. The temperatures of the cores of these fragments soared, and nuclear reactions ignited. Finally, the first stars in the cosmos were born, and light began to trickle back into the universe. However, these first stars were quite different to their modern-day counterparts. They were purely hydrogen and helium, and enormous. Many were more than 100 times more massive than our Sun. They would burn bright for a few million years, before dying in supernovae. Despite these brief lives, their intense light, mainly ultraviolet and X-rays, changed the universe once again. This radiation spewed into the cosmos, lighting up the heavens. But as well as this, as their high-energy photons smashed into the immense clouds of surrounding hydrogen, they tore their electrons clean off, re-ionizing the universe. More and more of the cosmos was transformed back into plasma, a situation that remains today. 99.9% of all atomic matter across our universe is in the form of superheated plasma. As these first generations of stars burnt, through their deaths, they polluted the universe. In their nuclear hearts, heavier elements such as carbon and oxygen had been forged, and through their explosive demise, these elements had been thrown into the black. The chemical enrichment of the universe was truly underway. And yet, throughout all these changes, gravity never changed, never faltered. It continued to draw matter together, and inhomogeneities continued to grow. Eventually, groups of stars fell together, merging and forming larger groups of stars. The epoch of the first galaxies had arrived. It's impossible to pinpoint exactly when a galaxy is born. Mass over densities seeded by quantum fluctuations are continuous, and whilst punctuated by the first stars bursting into life, the process of galactic growth continues inexorably. But grow they do, firstly through a steady accretion, and then through collisions of more appreciable chunks of matter. Cosmologists call these chunks halos, dark matter, gas, and stars bound by their mutual gravity. And as time goes on, scattered throughout the universe, more massive, gravitationally dominant halos emerge. These dominant halos become the site of future galactic growth, and as their gravitational influence grows, so do their dominance. More and more matter is drawn into their grasp, providing the raw material for building future generations of stars. These initial stages of galactic growth were quite uneven. The majority of these baby galaxies small and growing slowly, more massive and intense galactic growth much rarer. Indeed, this immense spread of galaxy masses is still imprinted on the universe today. And for the smallest of galaxies, these initial stages of life were quite dangerous. They could potentially host a massive star, burning brightly for a few million years, only for it to supernova, with the violence of its death expelling all other gas in the galaxy, the small galaxy's weak gravitational pull losing this gas into the universe. Its star-forming life ended before it had barely begun. Many of these small but extinguished galaxies would have inhabited the early universe, halos of dark matter devoid of all atoms and of all stars. These dead, elusive ghost galaxies were doomed to remain dark and unseen, and they should still fill our universe today. But more massive galaxies were different. In a larger galaxy, gravity could draw the gas back in, being recycled into the next generation of stars. And so whilst many galaxies were snuffed out in the early cosmos, others grew fat on the stars and gas they continued to consume. In their deep gravitational wells, new stars were born, lived, and died. But these were different to those of the first generation of stars. Through each generation of stars, heavier and heavier elements are expelled and pollute the cosmos, and these are recycled into subsequent generations. These elements represent barely a trace compared to the dominant hydrogen and helium, but their presence drastically influences the life cycles of their hosts. The heavier elements mixed into the layers of the stars change their opacity. This is a measure of how easy it is for the nuclear energy at the stellar heart to escape. And in trapping radiation, stars more similar to our Sun begin to be born, with longer lifespans and less explosive ends. As billions of years passed, some galaxies began to settle into a more sedate lifestyle. But violence still existed in the universe, a violence that began at the very start, a violence that would go on to create some of the most extreme environments in the cosmos. To understand these, and how the first galaxies became the galactic zoo we see today, we will have to first take a trip back to the middle of the 20th century, to a time when astronomers were facing a mystery on a truly cosmic scale. Karl Jansky was confused. It was 1932, the early days of transatlantic radio communication. The world was getting used to beaming voices over thousands of kilometers, but there was something about the signal.
What happened?
And so, we bring our understanding of the universe up to the present day, and our superficially calm lives within the fully grown Milky Way. Astronomers like Rodrigo have built their observations on the shoulders of giants, previous generations of astrophysicists and cosmologists working together to model and test how galaxies work, and reaching back in time billions of years to theorize how everything came to be. And yet, if you were to believe the headlines in 2022, all of this, from quantum ripples to theories of galaxy formation, may have been fundamentally wrong. This story opened with the mighty roar of a rocket on a Christmas morning and a new view of the universe. Shocked astronomers, galaxies that appeared to be far too large, too grown up, blinking back at us from the first billion years of the cosmos. One scientific paper even started its title with "Panic at the Disks," highlighting the shock that well-formed disk galaxies appeared in the infant cosmos. Soon, newspapers all around the world were announcing that the James Webb Space Telescope had brought an end to cosmology itself. Was our entire understanding of galactic formation under threat? Around the globe, cosmologists gnashed their teeth at the media attention and leapt to clarify what Webb had seen, what its observations really meant. And so, to understand this, we are going to have to delve into our current model of the cosmos, because it all boils down to one key question: what kind of universe do we live in? As many scientific stories do, we begin in the early decades of the 20th century. Einstein had thrashed out his general theory of relativity, our modern theory of gravity, and with others, such as Friedmann and Lemaitre, the equations that governed the cosmos were derived. These showed that the universe should be a dynamic place, expanding and evolving as it aged. In the 1920s, Hubble's observations showed this maths was an accurate description of reality. The galaxies were moving away from each other due to the expansion of space, and as galaxies must have been closer together in the past, there must have been a time where everything was together, a cosmic creation. Our modern cosmology, the Big Bang, had arrived. The relativistic cosmological equations, however, do not predict a single specific universe. In fact, there are an infinite number of possible universes mixed in the mathematics. So to single out our universe, astronomers needed to measure two specific things about the universe. Namely, how fast is it expanding now, and just what does it contain? The measured rate of expansion is known as the Hubble constant, and it tells you how quickly galaxies are moving apart based on their current separation. The separation of nearby galaxies is slower than those further apart, as there is more expansion of space between the two distant objects. Measuring the Hubble constant was a major observational effort of the 20th century, with astronomers forming factions around particular techniques and measured values of the constant. The process was complicated, as accurate measurements of galactic distances were required, and as the universe doesn't provide us with cosmic rulers, these were notoriously difficult to measure. For half a century, debate raged over whether the Hubble constant was 50 or 100, when expressed in cosmologists' favourite unit of kilometres per second per megaparsec. But by the 1990s, the power of the Hubble Space Telescope was brought to bear on the problem, and astronomers breathed a sigh of relief when the measured value was shown to be 72, about 235 kilometres a second per million light-years. So, with one of the key values determined, what about the content of the universe? This was an essential ingredient as the presence of matter and radiation drag on the expansion and steadily slow down the cosmos, with more material providing more of a deceleration. As this influences the age of the universe, astronomers were keen to measure just how much stuff there was. Counting starlight was relatively easy, as you can simply peer through your telescope and see the galaxies. But astronomers had come to realize there was more to the universe than the stars you can see. Observations of the rotations of galaxies and motions in clusters of galaxies showed there was much more. The mass of the universe was actually dominated by unseen dark matter. As dark matter is almost impossible to observe, astronomers decided on another path. They would chart the cosmic expansion as they peered into the distant universe, and by mapping this, they could determine just how much dark matter is pulling on expansion. By the 1990s, two teams set out, using the light of exploding stars as beacons, to do just this: the HiZ Supernova Search Team and the Supernova Cosmology Project. The observational challenges were substantial, again requiring accurate distances to make the measurements. Their focus was supernovae 1a, stars whose explosions appeared to be essentially identical, allowing them to calibrate their true brightness and so measure distances. And as the new millennium approached, they had their chart of the expansion history of the universe. But as they stared at the data, the astronomers were confused. They had expected, due to the presence of matter, the cosmic expansion should have steadily slowed. But whilst this had been the case in the early universe, in our time, it was not. And so they were faced with the question of what could be driving the expansion faster and faster. Looking at the relativistic equations of the cosmos, the culprit couldn't be matter or radiation. Something else would have to be added to the universe, a new form of energy throughout space. And this energy would have to have properties unlike matter or radiation, making it push rather than pull on expansion. This mysterious substance, not previously seen in observations, was dubbed dark energy. But it was not only the presence of dark energy that shocked astronomers, it was also the amount. They found that all matter, luminous and dark, accounted for only 30% of the cosmic energy budget, with this ubiquitous dark energy accounting for the other 70%. And as atoms in the form of stars, planets and gas make up about 5%, we truly live in a dark universe. Astronomers had isolated our universe from the myriad possibilities, the infinity of options. We finally knew what universe we lived in. They called this the Lambda CDM cosmological model, lambda signifying the presence of dark energy, while CDM stands for cold dark matter, the material that shapes the formation and evolution of galaxies. And it was with this they could precisely pinpoint the moment of creation, a Big Bang, 13.8 billion years ago. With the Lambda CDM cosmological model in hand, we can calibrate the universe. Light from distant objects is redshifted due to the expansion of space, and we can tie this redshift to the age of the universe when the light began its journey. Indeed, it is this cosmological model that tells us the James Webb Space Telescope is seeing galaxies in the first billion years of the cosmos. And so, do the observations of Webb really threaten our cosmological framework? The difficulty is that the mathematical equations of cosmology only tell us about the large-scale evolution of the universe, not the detailed flow of dark matter and gas into the first galaxies. To understand the growth of galaxies, we need to add more to the cosmological equations. And it is here astronomers face significant challenges, as the growth of galaxies depends on a wealth of factors. These range from scales of millions of light years, charting the flow of matter in the large-scale structure, down to observing individual galaxies and witnessing starlight through our telescopes. And we even need to add the fragmentation of gas clouds and the formation of stars into the mix. Not only this, but the first stars evolve fast and explode, blasting material and energy into the surroundings. All this needs to be tracked and traced in a swirling environment where massive black holes may lurk. Astronomers try to capture all of this complexity into a set of mathematical recipes, and these recipes represent our models of how galaxies form and evolve. But the key here is in the plural, as there is not a single preferred model to explain it all. The physical conditions and processes of the early universe are in part mysterious and unknown. Astronomers have to resort to approximations and even guesses in constructing aspects of their models. And it is the veracity of these models that is being put to the test by James Webb. In the short time that has passed since the claim of cosmology's demise, the excitement has died a little. Astronomers have realized that there is enough slack in their models to account for Webb's observations. A tune here and a tweak there, and the galaxies as spied by the telescope are not that surprising. Astronomers may have been led astray by some of the initial assumptions that were made. Take, for example, something that is known as the stellar initial mass function. This tells us the mix of stars formed when a giant gas cloud fragments and collapses. Typically, there will be a few massive bright stars and lots of fainter, smaller stars. But what if your stellar initial mass function is wrong? The stellar initial mass function is something we can measure and calculate in the local universe. But the assumption that it was similar more than 10 billion years ago is just that, an assumption. We know that at the earliest times the universe was very different from today. And so, what if the stellar initial mass function was also different? What if it was skewed and resulted in the birth of more luminous stars than expected? Then these baby galaxies would burn more brightly than expected, and astronomers would estimate that they are larger than expected. At the moment, not everyone is satisfied, but the feeling is there is a problem with models of galaxy evolution. The underlying cosmological model, lambda CDM, appears to be safe. Indeed, if James Webb is telling us anything, it's that the early universe was more complicated than we have so far imagined. And this is precisely what it was designed to do. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave us a comment to tell us what you think. Thanks for watching, and we'll see you next time. On Christmas morning 2021, a mighty rocket burst.
Cosmology is the study of the nature of the universe itself, arguably the most fundamental question astronomy can probe. How big is the universe? How did it begin? What is the universe at all? It's a field that can humble the most narcissistic of kings, one that inspires personal transformations from nihilism to humanism, and one that in recent years has been claimed to be facing a crisis so severe it threatens to undermine our very physical models of the cosmos. I am, of course, speaking of the Hubble tension, the so-called crisis in cosmology. Like any active area of research, this is one where the needle is rapidly moving as new analyses and data are pouring in on an almost daily basis. Yet despite all that, we do have enough information in hand now to say that something appears to be very wrong. So today, let's break down what is this crisis and what might it really mean. No sensationalism, just the facts. The story really begins in the late 1920s when observations of distant galaxies revealed that the further away a galaxy is, the faster it appears to be moving away from us. Both Edwin Hubble and Georges Lemaitre independently realized that the universe must be expanding in order to explain this. Like stretching a piece of rubber with marked points, every point thinks that every other point is moving away from it during the expansion, and indeed the points furthest away seem to move faster. In the early 20th century, the rate of expansion was difficult to reliably infer, but over the years, astronomers have improved their ability to measure this expansion rate, which has become known as the Hubble constant. The Hubble tension refers to a disagreement about this value. In particular, this number has been measured with two independent methods which seem to give answers which are sufficiently different that they are difficult to reconcile. Either one of these methods is wrong, or there was something wrong with our understanding of the cosmos itself. The first way we can measure the Hubble constant is from the cosmic microwave background, or CMB for short. This is the earliest light we can detect in the universe, emitted at a time when the cosmos was less than 400,000 years old, so that's 13.8 billion years ago. At first glance, the CMB appears remarkably uniform, with the universe appearing to have an average temperature of about 3 Kelvin in all directions. But subtracting off that average, the patterns and inhomogeneities that are revealed encode information about the shape, composition, and structure of the universe. Remarkably, just about everything within the CMB can be described by a physical model using just 6 free parameters, describing the mixture of matter, and dark energy, as well as the shape of the universe and its expansion rate. The agreement of this model to the data is frankly remarkable, with the recent Planck mission revealing almost perfect agreement to the model across the board. By running this cosmological model forward in time, one can predict what the current rate of expansion should be. Over time, we've got better at making that measurement, with early results from the WMAP satellite giving a result of about 72 plus or minus 5, but now more precisely pinned down to 67.4 plus or minus 0.5 using the Planck mission. I'll ignore the units here because it's really not that important for the current discussion and largely just distracts from the main points. The real thing to take away here is that all of these measures are within error of each other and look consistent with just improving our precision over time. So if this cosmological model is correct, which remember it does a remarkably good job of explaining the CMB data, then we really should expect that the modern universe around us is expanding at its predicted rate. But of course, we don't just want to trust the math. Astronomers actually want to double check that number. So we've been going out, taking the local universe around us and measuring its expansion rate to make sure that everything agrees. These methods largely build upon what Edwin Hubble was doing almost a century ago, measuring the distances and velocities of distant objects and putting them on a graph to get the expansion rate. The devil is in the details though, for measuring the distance to objects is particularly nuanced and challenging when dealing with objects that are millions of light years away. If I want to measure the distance to a nearby object, the way our brains do it is with parallax. Hold your finger out at arm's length in front of some distant background, like say a city skyline, and if you close one eye and then the other, your finger will seem to move from side to side relative to that background. That's because your eyes are in physically different locations, and so the angle subtended from each eye to your finger is different. The closer your finger is held to your eyes, the bigger the shift. However, as we move our finger away, the shift becomes less. So in this way, the parallax shift gives us the distance to an object, and we do the same thing in astronomy, except the spacing between our eyes is replaced with the orbit of the Earth from summer to winter. The Earth physically shifts by 300 million kilometers over 6 months. The Gaia spacecraft is a master of measuring parallax, and it has now done so for millions of stars. But the further away an object is, the smaller its parallax will be, eventually becoming so small that we can't detect it even with Gaia, To get around this, astronomers need a new distance measure, a distance proxy, and so that's where a special type of star enters the story, one called a Cepheid variable. All we really need to know is that Cepheids are massive stars that regularly pulse, causing their brightness to periodically increase and decrease. These are very bright objects detectable from across intergalactic space, and it was Henrietta Leavitt who discovered that their pulsation periods were intimately related to their brightness. Leavitt turned Cepheids into so-called standard candles, which are invaluable to cosmologists. The basic idea is that you first measure the distance to a nearby Cepheid using parallax, which, practically speaking, means it has to be one within the Milky Way in order for that technique to work. Step 2, very simply, you just measure how bright the Cepheid appears here on Earth. Step 3 is that you calculate then how bright the Cepheid must truly be given its distance using the inverse square law. And step 4, you observe its pulsation period. Doing this for all the nearby Cepheids you can find, you can make a graph of the Cepheid luminosity versus pulsation period, giving this tight relationship. That relationship, known as the period luminosity relation, or simply the Leavitt law, is kind of like your decryption key for measuring distances outside the galaxy. Because having calibrated this law, we can now go out beyond the Milky Way, take a Cepheid's pulsation period, and then immediately know what its luminosity must be. Combine that with its apparent brightness, and you can figure out how far away it must be using the inverse square law, so its distance. And that distance is one of the two basic quantities we need to know in order to calculate the local expansion rate of the universe. So you can see that this technique is very powerful, but eventually it stops working for galaxies beyond about 100 million light years. After that, the Cepheids are just too faint for us to detect in the first place. Now that might sound like a huge number, but remember the universe is about 90 billion light years across, so we'd really like to go much further. A key thing to keep in mind is that this technique is wholly predicated upon correctly calibrating the Leavitt law within the Milky Way galaxy. In this way, you can think of it as being like the second rung in a ladder, which depends upon that first rung, which remember is correctly calibrating that law. In fact, we could even go to a third rung, which depends upon the second rung, and in this case, that third rung is Type 1a supernovae. Like Cepheids, these are thought to be standard candles, objects with standard luminosities. But unlike Cepheids, we've never seen one up close and personal to really know what that standard luminosity actually is. Which is probably a good thing, because those events are so violent that a local instantiation would be undesirable, to say the least. And so in the absence of any local examples, we are forced to figure out the luminosities of these Type 1a supernova using the second rung of that distance ladder, so the Cepheids. In some galaxies, we see Type 1a's go off, and in those same galaxies, we also see Cepheids. That means that we can use the Cepheids to measure the distance to that galaxy, which of course means that that must also be the distance to our supernova. And then we can figure out how luminous the supernova was. So Type 1a supernovae are the third rung on the ladder, and they are so bright that we can look far further out into space, out to distances of now up to 1 billion light years away. But like a house of cards, if any of the layers below are wrong, then our calculated distances to the Type 1a supernovae will also be wrong. And that in turn means that if we use them to calculate the Hubble constant, that too would be wrong. It's a precarious game. If you want to measure the Hubble constant to a precision of say 1%, and that means that you need to calibrate each of those distance ladder rungs to at least 1% precision, or really even better. The chain is only as strong as its weakest link. So with our intro to the distance ladder complete, what does it actually tell us about the expansion rate of the universe, Hubble's constant? A team led by Nobel laureate Adam Rees, who call themselves SHOES, have been leading an effort to measure the Hubble constant of the local universe. Similar to what we're seeing with the CMB value, the precision has been increasing over time thanks to more precise parallaxes, refined analysis techniques, and more observational data, which, by the way, includes over 1,500 hours of time on the Hubble Space Telescope. As before, the fact that the value gets more precise really isn't surprising, and Each improvement agrees with the previous estimate to within error. So far, so good. But the problem is when we put the CMB measurements back on the same plot, we see a growing discrepancy between them. That right there is the Hubble tension, the crisis in cosmology. So something is very weird here. One of these measurements must be wrong. If it is the local universe one, then that implies that our distance ladder is most likely in error. There must be some systematic calibration issue with what we did there. But if it were the CMB one that was wrong, then that would imply that our cosmological model of the universe is itself flawed. That's perhaps the most exciting of these two options, because it would mean that there was new physics beyond the current model. So what could this new physics be? There's been plenty of exciting suggestions, such as a new particle ignored by the existing model, like the sterile neutrino, for example. Another popular idea is that the strength of dark energy is growing over time, which would have some important consequences for the fate of our universe in the distant future. Others have suggested decaying dark matter, or modified theories of gravity, non-zero spatial curvature, or exotic interactions between dark energy and dark matter. In fact, as you can see, there are quite a few options on the table, but before we start ripping up the physics textbooks and getting too excited, there is, of course, a far more mundane possible explanation, and that is that our local measurement is wrong, that perhaps the distance ladder has been miscalibrated. This isn't just idle speculation. There are good reasons to be worried about the validity of the distance ladder. First, although the leave-it law was indeed initially conceived to be a simple one-to-one relationship between pulsation period and luminosity, we've since discovered that it also subtly depends upon color and metallicity. That's frustrating because there's actually only a few dozen Cepheids in the Milky Way, so it's going to be difficult to precisely measure these new dependencies from such a small sample to begin with, as well as, of course, challenging to measure those same properties for other galaxies down the road. Metallicity is a particularly challenging topic because for Cepheids, you can't even often measure their metallicity directly. Instead, we rely on the surrounding environment's oxygen abundance as a proxy. The dependency of luminosity upon metallicity is characterized by this coefficient in the leave-it law equation. It's almost like the exchange rate going from dollars to yen. If you want to know the value of your yen, then you of course need to know the exchange rate to make an accurate conversion. The problem is that astronomers don't really agree on this coefficient, as shown by the range of recently published values shown here. And these differences can introduce discrepancies in the Hubble constant at the percent level. Now, there is some hope that JWST will provide a firm answer here thanks to its improved spectroscopic capabilities, but for now, we may have to wait. Another problem is frankly unavoidable. Cepheids are massive stars, which means they are young stars because massive stars simply don't live very long. So, why is this a problem? It's because stars are typically born in dense stellar nurseries that are nestled within their galactic disk. This is the New York City of the galaxy, a busy, bustling, dense, overcrowded region filled with dust and dirt all over the place. That dust, though, is a major problem, for dust blocks out some of the Cepheids' light, and so we have to carefully correct exactly how much light was blocked out. If we assume the wrong amount of dust, though, then we'll get the wrong luminosity for our Cepheid, and so break our distance ladder. Who would have thought that something as boring as calibration issues and dust could be potentially responsible for a crisis in cosmology? You hoped for a revolution in physics, and instead you got dust. Indeed, this might sound familiar because it's not the first time astrophysicists have experienced that sensation either. Remember Bicep 2 or Boyajian star, dust, and dust. So to some degree, this is an unavoidable problem with Cepheids. So perhaps one solution is just to ditch the Cepheids altogether, to start over, go back to the drawing board of our distance ladder, and get a new first and second rung. But to do that, we would need to replace the Cepheids with something else. We would need a new standard candle. Enter giant stars. Stars, like the Sun, fuse hydrogen into helium in their core, but eventually they'll swell by hundreds of times as they exhaust the supply of hydrogen fuel in their cores and instead start fusing the hydrogen around the shell of the core. This shell burning behavior leads to a rapid ballooning in the size of the star, which in turn causes the luminosity to greatly rise. It's exactly this process that will eventually doom us all here on Earth. Check out our previous video to see how. Eventually, the pressure in the stellar core becomes sufficiently high that the thus far inert helium ash starts to fuse. This is actually good news because the star is now burning fuel in its core once again, albeit helium fuel, and so now the star returns to a more stable state and thus a smaller size. So if you track the luminosity of the star over time, you'd see this gradual growth during the shell burning phase, followed by a reversal once the helium fusion begins. That reversal point, the peak luminosity, is called the tip of the red giant branch, and it's largely independent of the star's metallicity, unlike for Cephids. In essence, this reversal point is a standard candle. It's a weird one though, because it doesn't really work for any single object, since it's unlikely you'd happen to catch a star at exactly this moment in its life cycle. But if you look at the brightness values of a large number of giants, then you'd see a clear maximum possible value that corresponds to the tip of the red giants, and that peak is our standard candle. This method is in many ways cleaner than that of the Cephids, since unlike the leave-it law, there's hardly any dependency on metallicity here, which remember is very difficult to measure at cosmic distances. Yet more, another major advantage here is that these stars are by definition old stars. For example, it would take a star like the Sun about 10 billion years to get to this point in total when counting from its birth. Because of their advanced years, they have long since left their stellar nurseries and have meandered in and around their galaxy many times over. In fact, a large number of them no longer even reside within their galactic disks, but instead have migrated out to what we call the galactic halo, kind of like the quiet backcountry of the galaxy where the spacing between stars is far greater. This is incredibly useful because out here there's hardly anything to get in the way of our observations. There's no dust, there's no contaminating stars. If observing extragalactic Cephids is like trying to do astronomy in New York City, swamped by the haze and city lights, observing extragalactic giant stars is like being out in the Atacama Desert. Clear, inky black skies peppered with crisp oases of light. Famed astronomer Wendy Friedman has been advancing this method for years, which is not surprising given that it was she who first used the Hubble Space Telescope to measure the Hubble constant 2 decades ago using Cephids. Suffice to say, Friedman has been thinking about this problem very deeply for as long as anyone. So her team recently used this completely independent standard candle method, the giant stars, as a way of recalibrating the entire distance ladder in an effort to finally resolve the Hubble tension. On the one hand, we have the 67.4 plus or minus 0.5 value derived from the CMB using Planck, and on the other hand, we have the supernova plus Cephid-based measurement coming in at 73.0 plus or minus 1.0 coming from SHOES. So the real question is, where does this new independent measurement land? Does this third method reveal who's right and who's wrong? Here's their answer, right in the middle of the two. 69.8 plus or minus 1.7. Remarkably, it's actually consistent with both. Whilst the CMB and the Cephid measurements are 5 error bars apart, or 5 sigma, the tip of the red giant branch method is effectively okay with both of them. It's 1.3 sigma away from the CMB method, which is completely fine, and 2.9 sigma away from the Cephid measurement. That's a little high, but we could perhaps just explain that by adding in a little bit more systematic error into the Cephid measurements. In our upcoming Cool Worlds podcast show, which you can look out for in the new year, I asked Wendy what her reaction was when she saw that her measurement landed right in the middle. And I guess we were hoping that your number would land on one side or the other, and we'd be like, okay, so now we know where the problem is. When you realized your answer was right in the middle, were you frustrated by that? How did you feel?
Well, the immediate reaction was sort of like shock. Really? Did it really right in the middle? It was sort of odd, and we didn't attach this absolute 0 point until the end. So we didn't know where this was going to land until we were, ready to apply it. And that was it. It was like one morning, here's the answer. And it was slightly a shock.
An interesting way of thinking about the Hubble crisis is to imagine an alternate reality. An alternate reality where we invented and deployed the tip of the red giant branch method before the Cepheid method ever came along. So in this alternate reality, we'd have two measurements for the Hubble constant, one from the CMB and one from the local universe, and both of them would seem to be in almost perfect agreement with one another. There would be no tension, and instead we'd just be celebrating the remarkable fact that these two radically different methods gave remarkable agreement about the expansion rate of the universe. So if then Cepheids came along later, we would likely just dismiss it as a troubled method, especially given the fact that they are usually embedded within bustling galactic disks. So does this mean that there's no crisis in cosmology then? Well, before we totally give up on that idea, I think we still want to improve our precisions just a little bit more. On the horizon, there are two big data releases from the Gaia spacecraft that promise to improve our parallaxes even further, and thus will let us go back and recalibrate that distance ladder just a little bit better. Yet more, JWST is already observing nearby galaxies in an effort to measure their distances using both the Cepheid technique and with giant stars, as well as other methods too, to hopefully finally figure out whether they agree with each other or not. So rather than jumping the gun too much, let's just see what Friedman's team find from that sample. You know, a crisis in cosmology makes for a great headline, so much so that it's proliferated across many science news outlets over the last couple of years. It's probably why you clicked this video. And indeed, this video would surely get a lot more views if I told you that physics is broken, or that the Big Bang model is wrong, or some other extreme conclusion, or showed you thumbnails of JWST randomly firing death rays out of it or something. Yes, that really exists. But the truth is often more nuanced, complicated, and often less exciting than that tagline betrays. After all, the answer here may simply be dust. But a headline like dust may be a source of systematic error in Cepheid distance measurements just isn't as catchy as a crisis in cosmology. I can't give you the answers that you might want to hear. That's not how science works. To quote Feynman, nature is there and she's going to come out the way she is. Our predispositions don't count. All I can ever promise you on this channel is a sober analysis, but looking ahead, there will be answers here. From Gaia, from JWST, we will resolve the Hubble tension. So until then, stay thoughtful and stay curious.
Thank you very much. And we're going to now take a short break. McKinley, do you have anything to add before we go to the break?
No, let's take the break.
Okay.
When you
So-
pause the video, I'll have some.
Yeah,
announcements.
let's come back in 10 minutes. And welcome back from the break. I'm going to give the word first to McKinley and then discussion to Monty. Thank you.
Thank you, Simona. I had hoped to share a slide during the break, but I looked for that slide and I couldn't find it. But I want to say this. A few months ago, I was on a Sabbath afternoon walk with a good friend who is a wife of a pastor. And as we walked that Sabbath afternoon, I think I shared with her a dream I had had. But the conversation continued on to some other things as we normally do. And I said to her about the creation, I have zero doubt about the Genesis record. And most specifically, Genesis 1:1. In the beginning, God created. And My friend in response said to me, "That's a very strong statement." And I said, "Yes." And she said, "Why do you say that?" He said that I have thought about this very carefully, and putting on my hat as a licensed mechanical engineer who is a student of thermodynamics, I just find that the record of a built environment, a populated environment by the Creator is very, very consistent with the generalized laws of thermodynamics. And as the new information emerge about the struggles researchers are having with the existing standard model of cosmology, and the calls for revisiting it. An observation I'll make is that as researchers attempt to delete the role of the Creator in the cosmology, we are finding that the models that replace that idea or notion of a Creator have huge challenges. And so the question for all of us as Christians who are thoughtful people, rational folks seeking answers is, do we reaffirm our faith in the Creator? Do we look forward to the recreation and the remaking of the heavens and earth as the Bible talks about? Or do we continue to drift, feeling our way about, looking for answers about the origins of the cosmology? I hope our conversation today and the videos that we shared gave you some things to reflect on. Thank you.
All right, I guess that brings it to me. Thank you, McKinley. Dave, your hand is up and I will watch for other hands.
Well, I have something to say about how all that we have seen relates to the 28 fundamental beliefs of the church. But I can hold that off. Let's let other people go ahead first.
Stephen.
Thank you. McKinley, I want to thank you for the presentation. The first video was extremely powerful for me. I'm reminded, and Anastasia and I were talking about this, that God's creation is a constant continuum, and it's ongoing. And it's part of the whole, from our perspective, a part of the whole becoming. And I'll let Anastasia speak to her perspective on this too. But it's a reminder of how awesome and mysterious and just unbelievable our God is, and loving, and that we continue to walk in the footsteps that He has imprinted on our lives and our universe and everything. And as we discover, and I think the one thing that I'm reminded of is that in all of this, all the science and all the discovery, the importance of maintaining a constant sense of humility and a constant sense of openness to discovery and information and awareness. And as we do that, we begin to just scratch the surface, I'm sure, of God's creation. And these advances in technology, which God has gifted us with, enable us to find our way with increasing clarity, and it just reaffirms. And I think I would agree with your assessment. Genesis 1:1, in the beginning, God created, and it didn't stop. It hasn't stopped there.
All right, thank you, Stephen. And I don't have another hand. So Dave, I'm going to come back to you.
Okay, I'm going to try something here. All right, here we go. We've been talking about Genesis, and here is what it says. When God began to create the heavens and the earth was complete chaos, and darkness covered the face of the deep, while a wind from God swept over the face of the waters. Now, this does not say that when the creation events about which we have been talking were the origin of the whole universe. In fact, it has become standard thinking amongst Seventh-day Adventists, as well as others, is that the earth and the universe existed for we don't know how long before creation week as we understand it. So we need to notice that it says the earth was there. The earth was there, but it was complete chaos. And Stephen's point that creation began this time where Genesis 1 is, but it's continuing. And throughout Scripture, there are references to the continuing of creation. So that's right. Sometimes we hear the expression creatio ex nihilo. That means creation out of nothing. Sure, creation out of nothing occurred, but not here, much earlier than here. And that is not at all heretical. It's what is mainline Seventh-day Adventist teaching right now. So I think we need to be clear that when we talk about God creating this earth, we're talking about something different than when the whole universe began. Okay, that's the first point. Now, second point, when people ask me if I believe the fundamental beliefs, I say to them, I will never answer that question in a yes or no fashion, because words mean different things to different people. And if I said yes, you might misunderstand me. If I said no, you might misunderstand me. Therefore, I will write you an essay that tells you exactly what I believe, and then you can judge from your point of view whether this is enough. Now, it turns out that I can believe fundamental belief number 6, which is on creation, which makes 3 big points. Creation was recent, creation days were contiguous, and creation days were 24-hour days. Now, I could, if I were to write an essay on this, I would begin with 24-hour days. And I would say the meaning of this is that we don't believe, as some Christians do, that each day was millions of years old. I don't believe that. I don't think any Adventist that I know of believes that. That idea of the expansion of days theory is not something I believe. Therefore, I could say 24-hour literal days. I do believe that Genesis 1 is talking about 24-hour literal days. So I have no problem there. Contiguous, here, this word is denying another belief that some people have, and that is that there were gaps, the gap theory. There were gaps between the days of creation, which might have been millions of years long. And when one uses the word contiguous, one is saying, I don't believe this theory that says there were long periods of time between the days, just like I don't believe that each of the days was millions of years old. Those two things are pretty easy. Recent, that one is a bit of a challenge, and I would just have to say to them, yes, I believe that human life is recent, and I would go by the numbers, and I have checked them just this morning, a few moments ago. It is thought that the universe as a whole is about 13.7 billion years old. Planet Earth is thought to be about 4.5 billion years old. That's much more recent, okay? Life on Earth is thought to be 3.7 billion years old. Human life, 200,000 years old. That's very recent compared to 13.7 billion. But the most interesting number for me, and I looked it up again this morning, is that it is thought that human civilization is no longer than 6 to 10,000 years old. Now, most Adventists believe in a 6-day creation. You can see that. But we need to understand that, I think, in terms of the beginning of human civilization. And that is very recent. And it fits into a 6,000 10-year form. Now, that's what I would say. And I think some people would find it acceptable. Every time I've written a lesson, every time I've written an essay like this for the church, when it wanted to know what I believe, they've always said, that's great. Why don't you write that up in an article? So I've never had them, when I write an essay about what I believe, I've never had them condemn me. They always say, wow, we hadn't thought about it in those terms. Please write that up so others can benefit from it too. So I would write this essay. I'm sure some people would say, well, unless you believe that the universe as a whole is 6,000 years old,
Yeah,
I would say, well, not at all. The Bible is talking about human civilization, and that's not much more than 6 to 10,000 years old. Okay, that's it for me. Thank you,
Dave.
Monty.
Thank you, Dave. So I have Yoli's mic turned up, or mic unmuted, and I've got Peter's hand up. Yoli, did you have something you wanted to add?
I do, but I think Peter was first.
Yeah, but we've heard from we've been heavy on the men discussion. Let's hear from you, and we'll come to Peter.
Okay, thank you. I totally believe in God the Father as creator. I believe in Jehovah Elohim is my creator. I believe in Jehovah Adonai as the head of everything. I believe Jehovah Shammah is the Lord, is there, always there for me. I believe Jehovah Shalom is the only peace that goes beyond understanding. I believe Jehovah Rohi is my shepherd. I believe Jehovah Nisi is my banner, and I believe Jehovah Rapha is the God who heals. Moreover, I also believe Jehovah Jireh is the provider. As I say that, but I also don't understand always the conundrum between God and science. I think through God, I think God has blessed us with science in a way. I believe even God would agree, I surmise that God even would agree that men and women have improved greatly what he created. I'm just talking about things, the earth, the things like roads, rivers, seas, technology used to cure diseases, stop all kinds of sickness, have us flying to and fro thousands of miles in relatively small amount of time. But it also has these bad, we human beings. We use those technology to kill our enemies because we all want to be the first one to go somewhere and live forever. If God is not doing it fast enough, we're gonna try to do it ourselves by going to another planet, by this and that, because we want to live forever. I am really astonished and in awe when I pick up a little phone and I'm talking to my brother who lives in France. There's no visible wires, and I hear his voice like he's standing next to me. Men did those things. Those are wonderful things. And of course, there's gonna be, disparities because we are human beings. But I think we don't have to, it has to be either God or science. I am grateful for both, but I love my God, and I believe none of us could erase God from our heart because it's part of our DNA. I've been upset. I've cried to God, God, why do you let so much happen? I mean, well, and all this, but I cannot say for 1 second I stop loving God because I think I would just evaporate if I let that happen. And I love you all, and I mean that sincerely. And I hope God protect us and give us everything we need to just be at peace and enjoy our lives.
Thank you,
That's
Yoli.
all. You're welcome.
Thank you. And for reminding us of the amazingness of the things that are around us. It is truly amazing. I see Peter and McKinley and David. So Peter and then David, and then we'll come around to McKinley.
It's actually Simona.
Thank you,
Oh, sorry,
McKinley.
Simona. I didn't know you were Branson today. Okay, Simona. So Simona, you will be next. So Peter, then Simona, then David.
Thank you, McKinley, for your very interesting presentation. I believe that the scientists should have not been surprised that when they discovered that the universe is expanding, in other words, that God is still continuing his work, because Jesus revealed that to us when he was here, when he told us that my Father is still working until now. Then we knew that God continued his creation and maintaining the universe that he created. I have a few questions. I will start with 2 questions. First, one is McKinley, you used in your presentation in the beginning 2 words, cosmos and universe. Do you see any difference between them, and or they are just 2 words for the same thing? Or if you see any difference, what differences between them do you see? And the second question is, do you see any relationship between matter and mind? And if they were in existence in the same time, or one was preceding the other? I will stop here with these 2 questions, and if we have more time, I have some other questions.
I will keep you on the list, Peter. Thank you for that. And McKinley, a couple questions for you there.
Thank you, Peter, for your thoughtful comments and the questions. So the first question, is there a difference between the cosmos and the universe? I think in the sense, well, I think there might be a difference in the sense that researchers have postulated the possibility of multiverses. And I would look at the cosmology as containing a set of those possibilities. So there's a difference between, in my thinking, between the idea of a universe that has all of these stars, galaxies, planets, and other celestial objects, and the prospect of there being several universes. I think as I watched these videos and as I've applied, concepts like Markov chains and the so-called Fibonacci sequence, the immensity of the universe overwhelms and impresses. And so I would use the cosmology to apply to all of the possibilities of celestial bodies. Second question, in a relationship between mind and matter. So yes, I believe there is a relationship in a distinction. I think mind to me suggests a set of a framework for processing information. And matter, of course, would be a physical substance On the other hand, there is a relationship between matter and information and energy, as you've observed me present in our digital foodless potluck, and characterized through or by the generalized laws of thermodynamics, where information is equal to matter is equal to energy. So yes, I would make a distinction between the two, but then there is a connection in the generalized framework of thermodynamics. I hope those answers are helpful.
Okay, thank you. Thank you, Peter, for those questions. And we'll come, still got you on the list. Simona and then David.
So, perhaps difficult questions. How did space come to existence? Was it through expansion or through sudden creation? Because it seems that everybody thinks that from the moment of, let's call it Big Bang or creation, there is an expansion of matter. But what about the space? Since space-time is a continuum, we're talking about the moment when the time became. That means the space became. Second question is kind of tied to this. In the presentation, they mentioned that the universe that we know is about 90 billion years across. What is beyond that? Is universe truly limited? And if it is, what is beyond 90 billion years, light years?
Are those questions for me, Simona?
Yes.
Okay, thank you for your questions. Okay, so your first question, I think, goes to the consideration of boundary conditions. You asked, when did space-time come into existence? I think that there was a void, and at the moment, if I were to use the COBA, the Cosmology by Articulation model, before there was an articulation that specified the emergence of our universe, there was a void, there was an emptiness. And the articulation by the creator brought into existence space-time. And that would satisfy the boundary condition. On the other hand, if you use the postulated standard model, they would say, suggest that into that void emerged these quantum fluctuations that then gave rise to space-time. So that would be my answer to your first question. And then the second question, what is beyond 90 billion light years across? I think when one considers the possibility of the Markov chain, let me just define that for those of us who are not familiar with the Markov chain. So the Markov chain is defined as a countable infinite sequence. So if you consider a countable infinite sequence and combine that with the Fibonacci sequence, it is possible that a 90 billion expanse is not the limit. So what is beyond 90 billion light years? I would suggest a possibility of greater expansion. As the video and the narrative suggests, the universe is a churning out galaxies and so on and so forth. So beyond the 90 billion years is the possibility of greater expansion.
I just maybe just a talk on this. So what do you
Yes.
mean by void? That's the term that, you know, in some way still defines space. And secondly, if there is expansion, what is the center of that expansion?
So a void for me, as I'm using it here, would be a vacuum, kind of an emptiness. There's just nothing there. And so the concept of space-time implies an inertial reference frame that necessarily has a boundary. And the other question about what would be the center of space-time, I think.
If there is an expansion, it has to expand from somewhere. So what is the expansion, from? What is the center of, let's say, Big Bang, where it started in the universe as we know it?
Where it started. I don't know that I fully understand the question, but let's assume that there is this 90 billion light years of a radius or a diameter, for example. Mathematically, it's possible to identify, assuming again this Big Bang occurred, what the source or the original point of this explosion that's postulated might have happened, and from which all of these other processes emanated. Does that help?
Yeah, my question is, where is it?
Oh, well, okay. So what I've read is if you're thinking about a universe, there is a singularity that's called Sagittarius A. And it is kind of right smack in the middle of the universe as it has been postulated.
Okay, thank you.
Exactly, it does.
Thank you. Okay, let's see. So I'm going to go to David and then Anastasia. David.
Yes, McKinley, this is for you. A lot of the presentation went over my head because I'm not schooled in astrophysics, but I do have two questions for you. If you could just clarify the second law of thermodynamics as it pertains especially to entropy. What do you see as the difference of how that second law is applied for the standard model of cosmology versus the newer models? I gather the newer models give you more courage or bolster your conception that of intelligent design, that God is the creator. But that leads me to my second question. Could you be specific about what it is in the newer models that makes you see that God is the creator as opposed to the standard model?
Hey, I'm writing your questions down here. Okay, so thank you for the two questions. Let me address the second one, and then I'm going to try to come back to the first question. So the Cobra model is based on this generalized framework of thermodynamics that relates information,
Oh, I think I saw that.
energy, and matter. Okay. The standard expression of the laws of thermodynamics is matter and energy are neither created nor destroyed. They're equivalent forms of each other. The expansion of that is to add in information. And when information is added to that framework, we observe that humans create by thought or by information, and by the expenditure of effort, energy, we procure matter or mass. And the example that I've used in these types of conversation is think about a building or a car. How do they first begin? They begin as a thought. They begin as information. And following that information step, energy and effort are expended. That leads into the procurement of matter or mass, the materials that go into constructing your home. But all of that begins as information. Similarly, that can be expanded to the concept of the universe coming into existence. If one were to not only think about building a house or building a car, but were able to articulate that outcome, and if one were at the level of a creator, to bypass all of those intermediate steps and bring into existence that physical object, the generalized law of thermodynamics would be satisfied. Today, we see that we can speak to an Alexa, or speak to a Siri, or speak to a, I don't know what the other one is, but we can now articulate things into existence. And if one were at the level of a creator, to bring cities into existence, to bring complexes into existence, the generalized laws of thermodynamics allow for that possibility. And so when that construct is applied to the universe, it is essentially defining a pathway. It's not necessarily specifying the specific steps, but for me, it suggests that there is a pathway to that physical outcome along information, energy, and matter. I hope that first answer is helpful. And I'm sorry that I don't have that one slide that I wanted to share during the break. But if you were a part of the Digital Foodless Potluck, where I did a deep dive into all of these steps, including the quantum mechanics behind the wave equation and so on and so forth, it clearly is a possibility. Now, one other thing that I would observe is this framework provides a beginning point that the standard model does not provide. The standard model just says and assumes that things came into existence spontaneously. But there is, at least as I've understood it and from the literature I've reviewed, there is no equation that I can point to, like the definition of work and the first laws of thermodynamics, that lead me to that outcome or lead me to that starting point. Okay, so let me go to your first question. How does the second law of thermodynamics as applied to entropy relate to the existing standard model? Well, so we understand that the total entropy in the universe is increasing. But if the entropy in the universe, the total entropy of the universe is increasing, how is it possible for order to emerge as we observe around the universe from a chaotic situation without the input of information and energy? The second law requires that for entropy to be reversed, information input must occur and energy must be exerted or expended. The standard model, as far as I understand it, does not satisfy those requirements. They say that quantum fluctuations happen spontaneously, create entropy, and out of that entropy, order arises. But at the same time, in a sort of a contradiction, entropy is increasing. Anyway, I don't know if that answers your question, but that's my attempt at answering both.
Well, I was just wondering if you could clarify a little bit more in the newer models, though. How do you see the the second law of thermodynamics making more sense? And how does that lead you to a greater understanding that God indeed is the creator?
Right. So the second law requires that information be input into a chaotic situation for an order to emerge. The articulation of embodied, and this is where it gets a little bit, how shall I say, not wonky, but maybe confusing, but the articulation of embodied specification. Again, think about speaking to a Siri or speaking to an Alexa. What gave me insight into this idea was a lab that I visited been over 10 years now. They were building a tank, a fuel tank for natural gas trucks. The tank was printed on a 3D printer. The only thing that was required for the engineer at this facility to bring about the printing of that 3D product was to press a button. He could have easily spoken to that computer to bring about the production of that natural gas tank. But his speech would have included all of the specifications that then activated the printer to produce that tank. If you're able to join us next week, I'll plan to have the slides. If you can stay around for the first 15 minutes of the potluck, I'll share those slides again, and we can go into this a little bit more.
All right, thank you, David.
Thank you.
Anastasia, and then I'm going to put myself in the line, and I still have Peter on my list.
Thank you. And please, David, make sure you write that article. Many of those questions about the universe and divinity and logic and purpose and all this, actually very much what David said. Some other time maybe we should. Anyway, there is present at what they're called the pre-Socratian philosophers and scientists. One of them is Heraclitus, before the 5th century BC, the 6th century BC. And Heraclitus, where others, and right on my mind is foggy, they were discussing about the divine when there's so much chaos in the universe. And remember, at that time, they didn't have telescopes. So there is a Holy Spirit, a prophecy like in the Revelation about new things and so on and so forth. So what Heraclitus said in his observation that, yes, the universe was in flux. It was not static. And within that flux, there was a lot of destruction and recreation of things in the process of the divine creating. Nevertheless, what he observed is that in that chaos, in that flux, there was order and an intelligence. And that was the mind of a demiurgos. And we have two words again in the Greek, in the Old Greek. Demiurgos is the creator who has materials that he creates. Now, either he made them, he doesn't say they were there or anything like that, but he's a demiurgos who, with matter, he created the universe, the cosmos. At the same time, and we see that in the New Testament, when we have the Lord's Prayer, he says P-E-Ts, which in English is the poet, which is, and Heraclitus says, at the same time, this creator, that's also the word P-E-Ts means creator, but it's a different kind of creation. And that's the one, the inspirational one, the one, it's not even inspirational from outside or in itself. So God it's very possible that God didn't take it from any places, but in his being a poet, a pietist, within his demurrer, his creation, he conceived, he had, it came from inside him. He created like a poet, and with a beauty. And that's Heraclitus. And so, and then later on, Pythagoras, about the divine, through his numbers and mathematics, make the sense of that divine, yet logos, and on and on and on. And it's such a misconception, like David said to us when we talk about the Greeks. You know, many talk about the same Greeks. They talk about the Olympians, actually minority of those philosophers and scientists and so on and so on. They use them like we do things in Halloween to explain maybe good and evil and this and that. But they had serious conversations and discoveries about that creator they didn't know. And that's why when Paul went there, he says, to the unknown God. I thank all of you. And so much from what you said, David, and you showed, and those are the things that I saw in the Adventists when I first met them, about the creation, that it's logical, it's more than possible, and it's, yeah, divine inspiration. Thank you.
Thank you, Anastasia. Simona, Lisa has just drawn my geeky mind, which is enjoying this topic, to the fact that we're approaching 1 o'clock. We are way over our normal time.
We are fine.
Several people in line, but
let's get everybody who has raised their hand, and then we'll end.
All right, I'm going to step out of the line. I've got, let's see, let's come back to, oh, we only have repeats now except for Bronwyn. So I'm going to go to Bronwyn and then Peter and then Dave. We'll let Dave have the last word. Bronwyn, Peter, and then Dave.
Thank you, Monty. I was trying to put my video up and I can't find how to, oh, here we are. Okay, thank you. McKinley, thank you for today's discussion. I mean, it was wonderful. And Dave and I watched a video, actually a TV program through the week. It was 42 minutes long on how the James Webb Space Telescope was built. If you get a chance to watch it, it's really well done. And having watched that and then seen the videos today, it really helped a lot. Referring back to one of Peter's questions for McKinley, that, oh, I've lost it again. Here it is. About the question between the cosmos and the universe. As I often like to do, looked it up on Wikipedia, and I like this answer. It's simple and it helped me to understand it. Cosmos is a whole harmonious and orderly system that is governed by the natural law, while universe is everything that exists, including time and space, matter, and the laws that govern them. That was helpful.
Thank you. Oh, yes. Are you done?
Yes, I am.
Thank you for sharing those definitions, and I think it shed some light on the distinctions between the universe and the cosmos. One could potentially suggest they might be interchangeable. I think that's the word I'm looking for. But yes, I think again, just thinking about the immensity of space and at the level of the creator, the kinds of things that are possible, just make this a topic of deep reflection and and thinking about, and the desire to understand it more. And I've just been delighted by the questions and the conversations that we've shared. And you're right about the James Webb Telescope. It's a marvel of engineering. And to think that it took 30 years for them to, design and build that stuff. Now, the fascination for me is that, again, at the level of the creator, think if we as humans had access to the level of energies and the information, the capacity to speak such an object into existence. That is the really mind-blowing type of a possibility that I see that the generalized laws of thermodynamics make possible. Thank you for sharing that.
Thank you.
Peter.
Two quick questions. First, in one of his visions, the Apostle Paul is talking about him taken to the third heaven. In light of what we know about the cosmos now, and the fact that one experiment was done, I understood that one rocket was launched and it was believed that reached the end of the universe. But later on, the scientists discovered that beyond that, there are many other galaxies. Did you ever think what this third heaven could be located? Where is the place where God resides? The second question is, and it's more like meditating about the models that we have about the creation of the universe, and especially we have this Big Bang that it's most scientists believe in. This implies a terrible explosion that we cannot imagine. And this explosion emitted energy, emitted light, and hard to understand temperature. And in light of all this, I mean, the anarchy, because an explosion, it doesn't create order, create anarchy. How was possible? Because God was the center of this place where all this started. Wow, this terrible explosion, about this light and this temperature, high temperature. How is possible even to think that God continued to exist? We have a little bit something to think about how this terrible thing could have been. The explosion of two atomic bombs at Hiroshima and Nagasaki. And we know that this, I mean, the temperature and the light and the energy and everything was so destructive that people were just melted down, disappeared completely. And now we have atomic bombs that are 14 times more powerful than that. How this was possible for God, that was at the center of all this, to not be affected at all?
Thank you, Peter, for your questions as usual. Very stimulating. The first question, where do I think the third heaven is? I don't know. That's a short answer to that question. But I think, again, with the vastness of the universe, as we've been exploring, our God can reside wherever he deems suitable for his pristine environment. The second question about the explosion from which the standard model postulates the universe emerged from. I think it points to one of the mysteries that researchers are exploring, but also at the magnificence of how all of this came into existence. What I imagine, again, relying on this generalized law of thermodynamics, where information is equals to energy is equal to matter, that in the articulation of the universe, it may not have been necessary for a whole gigantic explosion to occur. And one way to think about that is much of what we see around our world starts small. We begin as, what's the word, Simona, as cells?
Zygote.
zygotes and grow into full maturity. Trees start as seeds and grow into orderly forms. Now, this part of my answer is speculative, but not entirely inconsistent with this generalized law, which involves the articulation or the speaking into existence of energy and matter. But you do raise an important point, which is one that I alluded to in the introduction, which is how can this order arise out of this chaotic explosion? And at the same time, the researchers suggest the total entropy in the universe is increasing. But you can see from this conversation how there is so much to explore with these new insights. And I think that is one of the reasons why people are being sad about the class coming to a close. These are things that in the long form of our digital footless potluck, we were able to explore over hours of conversation. I invite you to continue looking into these things for yourselves, because there's a lot of exciting things to discover. And that is why I'm looking forward to the new heavens and the new earth and life eternal, because there's just so much to learn. Thank you.
Okay, Dave, we are back to you and then back to Simona.
Okay, 5 very brief comments. First, I was struck by McKinley's use of the word articulation. And that reminded me of words. And that reminded me of logos. And in the beginning, in the beginning there was the Word, and the Word was God, and the Word was with God, right? So articulation and logos strike me as very close. First point. Second point, rummaging around, trying to understand all this that McKinley has presented, which is, I agree with David, is overwhelming for me. But one thing I saw some NASA scientists saying is, well, maybe there's not one Big Bang. Maybe there are several. Maybe it was the expression of firecrackers bursting or into flame many places. So that's a whole other way of thinking it for me. Thirdly, I think we need to go back to the Greeks again, not only for the notion of logos, but for the notion of cause. And the Greeks said everything has 4 causes. The material cause is the stuff out of which it is made. The formal cause is the architecture of it. I think that's what McKinley's talking about when he talks about articulation. That's the formal cause. That's the architecture. Stuff by itself isn't anything. It has to have some form. Thirdly, there is the final cause, which is the purpose for which the thing is made. And finally, the efficient cause, which is the energy that is required to transform the material cause into the formal cause so that it can be used in the proper way. So I think the Greeks can help us a lot there. Okay, that's
great.
David, you described the pre-Socratic philosophers right now.
Yes, we can learn from them a lot. And thank you for both of you for bringing this to our attention. Okay, next point. The plane is going to land next week, but it's going to get back up in the air. And we are going to get together either April 6th or April 13th. And we will set it up with a Zoom. I almost said spoon. Zoom. So that people who aren't in town can participate, and we're going to have a good time. So we're not going to end. People have made it possible for us to continue to meet, and we will meet, but it will be on the afternoon, and we will have a meal together, and we'll have a good time. Now, all of you have done so much for this class, and I thank all of you for it, and I will do so again next week. But here, right at the very end, I would like to thank one person in particular, not because this person is more important, but I think this person has made a very distinctive contribution, and that person is Simona.
Yeah.
Her entrances.
Yes.
Don't you think?
Yes.
She's an artist. She's an artist.
She has a
The way
calming
she
voice.
does. So I am so thankful for the artistry that Simona brings to moderating these sessions, and we will keep turning to her for such help in the future. That's it.
Okay, you have made it difficult for me to speak. Thank you so much. I am touched by your generosity. I am going to reveal a secret. My question to McKinley was a trick question. And the reason why it was a trick question is because the universe actually has no center. And it has no boundary. It has no limit. It is just our point from which we are looking at things, that things seem that way. And the space became at the moment of creation. So that's, these are a little bit trick questions, but I think lots of astrophysicists would agree with me. I'm going to end this session with a poem entitled Winter Stars by Sarah Teasdale. I went out at night alone. The young blood flowing beyond the sea seemed to have drenched my spirit's wings. I bore my sorrow heavily. But when I lifted up my head from shadows shaken on the snow, I saw Orion in the east burn steadily as long ago. From windows in my father's house, dreaming my dreams on winter nights, I watched Orion as a girl above another city's lights. Years go, dreams go, and youth goes too. The world's heart breaks beneath its wars. All things are changed, save in the east the faithful beauty of the stars. And our benediction for the week. May you find peace in your busyness, in your journeying, in your happiness, in your suffering, in your fearfulness, in your questioning, in your faithfulness, in your worshiping. May you find peace. Thank you, and I'll see you next week.
Thank you. Amen.